Welcome back to part 2 of Monday's lecture. We're going to be continuing on with our discussion of the energy principle for extended systems, still focusing on the spring mass system. All right, so as we all know, the best way to learn physics is to just do a lot of examples. So I'm going to give you yet another example. All right, so we have a system where we have a 17 kilogram mass. It is falling. It has an initial speed of 9.8 meters per second. Notice it's not meters per second squared. This is the speed, not the acceleration. It has an initial height of 2.1 meters. Now, it is falling towards a spring. This spring is presently relaxed, and it's presently 1.2 meters above ground. So we've got 1.2 and 2.1. So this is our setup. All right. So the block will strike the spring at 1.2 meters above ground. The spring has a K of 4,200 newtons per meter. Okay, so this is our initial setup. So we know that the spring, the mass is going to hit the spring, it's going to compress it, and then we imagine that eventually the spring will fling the block into the air. So there's a couple of things we want to know. So the block continues down. After spring strike, and it compresses the spring until it's 0.82 meters above the floor. All right, so for this particular situation, so that's going to have an R final of 0.82 meters. So we want to know, what is the speed? All right. So to go after this, we need to go ahead and set this up. So our system is going to be the Earth, the block, and the spring. And we have been clever in our choice of system so that we have nothing to do work on it in the surroundings. We always want to make our lives easier. Any place we can add a 0 and it be correct, it's generally the approach that you want to take. Okay, so the initial state is given in the problem. It's 2.1 meters above the floor. And moving downward with initial velocity of 9.8 meters per second, and the spring is relaxed. Now remember, the spring is a part of the system, so we need to make sure we're accounting for its energy at any given time. Okay, and in the final state, the block is at 0.82 meters above the floor, and the spring is compressed. So it's going to have at least a little bit of potential energy. Okay. So, and what we are going after is we want to look at the speed of the block in that. So we want VF final for this final state. Okay, so this is our setup. Let's move along to the energy principle. So energy final is equal to energy initial plus any work done. All right, so let's flesh this out further. We're going to need the kinetic energy final. Now, we've got three objects in our system. We've got the spring, the earth, and the mass. So we're going to want to look at those kinetic energies. So we're going to need the spring potential energy final plus the potential energy due to the force of the earth, gravity, final, and this is going to be equal to the initial kinetic energy plus the spring potential energy initial plus the potential energy from gravity initial plus any work done. Now, all right, now where are my zeros at? Because, you know, let's make our lives easy. All right, nothing is in the surroundings that can do work on it, so there's a zero there. The spring starts out relaxed. The block hasn't hit it yet. So if we go back to our setup here, this is the initial setup. The spring's just hanging out, not compressed, zero potential energy. All right, so there's another zero right there. Okay, so the term that we are solving for is still embedded. So let's go ahead and flesh these out. So 1/2 mv final squared plus 1/2 k sub s squared final plus mgy final is equal to 1/2 mvi squared plus mgyi. All right, so the term we want is that final velocity that's hanging out right there. So we want to algebraically manipulate, get everything over to the other side that is not the final velocity. So algebra commences, and we see that our final velocity squared is equal to the initial velocity squared from this term here. This 1/2 and m have canceled out that 1/2 and that m, plus 2 times g, initial minus final. This comes from having subtracted that term over and then factoring out the factor of 2 and g. The 2 is coming from this term, and that m has canceled out those m's. Minus k sub s, so since we've divided everything by m, this must now be divided by m, s squared final. All right, so v final is equal to the square root of v initial squared plus 2g y initial minus y final minus k sub s over m s squared final. All right, so now we can plug and chug, everybody's favorite part. V final is equal to the square root 9.8 meters per second squared plus 2 times 9.8 newtons per kilogram times, that's the difference there is 1.28 meters minus 4,200 newtons per meter divided by 17 kilograms times that stretch, which ends up being 1.2 minus 0.82 quantity squared. And this gets you a final velocity of 9.244 meters per second. There you go. Okay, so The next thing we want to find is we want to find the maximum height. So I'll go ahead and use a new sheet of paper. So what is the max height? If we go back to our initial setup, we know that the block is going to come down. It's going to compress the spring, and then the spring, being that it's now been compressed, it's got a bunch of energy, it's going to want to then re-lengthen, and eventually it's going to fling the block up into the air. And we want to know how far is this spring going to fling the block up into the air. So this is not the maximum amplitude of the spring, this is the maximum height that the block is flung. Okay, so our system and surroundings can stay the same. So our system, earth, block, spring has an R in it, the surroundings, nothing of interest, nada. Okay, but we do need to be clever about our initial and final states. So we can use whatever initial state we want. I'm going to use the initial state given in the problem setup. So let's just keep that the same. So 2.1 meters above the floor, moving downward with a speed of 9.8 meters per second, spring relaxed. Energy conservation always works. So let's use that. Our final state is going to be the block at the highest point with the spring relaxed. Okay, so this is our energy principle. So final energy is equal to initial energy plus any work that's being done. Let's flesh this out. Kinetic energy final plus potential energy from the spring final plus potential energy from gravity final is equal to kinetic energy initial plus potential from the spring initial plus potential from gravity initial plus any work done. All right, where are my zeros at? Okay, we know work is a nice big 0 for this setup. All right, it starts off with the spring relaxed, so therefore potential energy from the spring is 0. And the potential energy, so it says that the spring is relaxed at the end too, so there's another 0 there. What about that kinetic energy final? So when the block or mass has reached its highest point, it's going to come to a momentary stop where the velocity is going to be 0 before it descends back down. So therefore, for this setup, we have chosen the kinetic energy final is going to be 0. This is why problem setup is important. You can really make your life easy. Okay, so it's the only term we have left over here. So we've got mgy final is equal to 1/2 mvi, or v initial, plus mgy initial. All right, so we note all of these terms have the mass in them, so goodbye mass. We can divide you out. Now, of course, this is what we want. So y final is equal to y initial plus vi squared over 2 times g. And this is equal to 2.1 meters plus 9.8 meters per second quantity squared divided by 2 times 9.8 newtons per kilogram. And this is equal to 7 meters. So the block will be flung 7 meters into the air as a result of this. And we got this all from using the energy principle and taking advantage of the fact that the final energy is equal to the initial energy. And now you can see that just like in the momentum principle, objects carry with it the history of where it's been. This is also true with the energy principle. It carried with it the history of that spring. All right, there were some approximations we did make in this particular setup. So we neglected air resistance. We neglected air resistance. We ignored energy dissipation by the spring. It's not an ideal spring. And we use the approximation for gravitational potential energy near Earth's surface being equal to mgy. And that's a perfectly reasonable estimation to make, as we saw in Chapter 6. And we assumed that the change of kinetic energy from the Earth is negligible, which is a exceptionally reasonable explanation to make. I mean, you're not measuring that one. That's not changing the setup. All right, just to note, you might have said, well, why did we use the same setup as our initial state as before? The answer for that is, well, it's easy. But you could have used the final state from part A as your initial state. And you would have gotten the same result on your own. You should try this. Okay, so moving along to non-helical springs. So this is a helical spring. You can see it's going around, nice little helix. Because our idea of thinking of things in terms of springs is bigger than just what we conventionally think of as springs. So this is helical. All right, so we have previously treated bonds of metal as though they were springs. So it's metal, treat as spring. And this comes from the ball spring model of matter. You've got all of these little atoms, and they're bonded together, and they're stretching and compressing just like springs. So, and to go after the spring constant for these essentially solid materials, we used Young's modulus. So, we used Young's modulus to go after deformation. So if you recall, you had tension force over area is equal to Young's modulus times the change in length over the original length. And we can rewrite to parallel spring equation such that force is equal to Ks times the magnitude of S. And so tension force is equal to Young's modulus times the surface area divided by L times the magnitude of delta L. And all of these constants are materially specific, just like the spring constant. So this works even for modeling regular matter as a spring. All right, so Next up, we have section 7.3, so I'm going to end this lecture at a natural breakpoint, and I will see you next time.